Welcome to this lecture. This is part 3 of chapter 3, the chapter on first order systems on process control. In the previous part, that is part 2, titled as PC35, I had explained about the process of process that is happening in the thermometer, the variables involved, and the assumptions. So these have been explained in my previous lecture titled as PC35. So this lecture is a continuation of the previous lectures. The link for this previous lecture is given above and also in the description below. Well, if you see the thermometer kept in a bath, and X is the bath temperature, Y is the reading shown by the thermometer at any time. So the heat transfer takes place from the bath to the mercury in the thermometer, from the bath to the mercury. So we also said the entire heat transfer resistance is in a thin film surrounding the glass bulb of the thermometer. Well, this has been explained further in detail in the previous lecture. Now, what is the process that is taking place? Heat transfer. So at any instant after the disturbance is given to the bath, the temperatures are X and Y. So X and Y are at the unsteady state temperatures. At steady state, there will be Xs and Ys, that is before the disturbance. Now, this being a heat transfer process, so let us write the energy balance equation or heat balance equation. Energy balance or heat balance equation. So before that, let us define these variables. M is the mass of mercury in the thermometer. C is the heat capacity of mercury. H is the film coefficient of heat transfer. So heat transfer taking place from the liquid bath across the film to the mercury. So that heat transfer coefficient is film coefficient of heat transfer is H. And then A, the surface area of the bulb for heat transfer. The bulb is here, glass bulb. So since the heat transfer takes place across this bulb, the heat transfer area is denoted as A. Now let us write the energy balance equation. The heat transfer equation, energy balance equation is rate of heat input equal to rate of heat output plus accumulation. Rate of the heat input equal to heat output plus accumulation. So what is the heat input? Heat is transferred across this bulb. It's a convective heat transfer. So heat transfer across convective heat transfer flux is HA delta T, H into A into delta T. Here delta T is X minus Y. X here and Y. Heat transfer takes place, the temperature difference is X minus Y. X is the bath temperature, Y is the mercury temperature. So HA into X minus Y, that is going to be the rate of heat input. The heat input is HA into X minus Y. Now what is the rate of heat output? Where does the heat go? The heat transferred across from the bath to the mercury is entirely absorbed by the mercury. All the heat is absorbed by the mercury. So the heat output is 0. There is no heat output. There is no heat output from the thermometer to anywhere. So the input is this HA and X minus Y, output is 0. And rate of heat accumulation is d by dt of mcy. M is the mass of mercury, C heat capacity, and Y is the temperature. So the total mass, total capacity mc into the temperature mcy, d by dt of that will give you rate of heat accumulation. Well, So M and C are constant, so I take an MC out. So this is equal to MC into dy by dt. So this is the energy balance equation at unsteady state. Unsteady state means after a disturbance is given, that is T greater than 0. After a disturbance is given, when the bath temperature is varying with respect to time, that is unsteady state. So this is the heat balance equation at unsteady state. Now we have to write it at steady state. Now steady state, the equation is the same. Only thing that at steady state there is no accumulation. At steady state there is no accumulation. This term becomes 0. This term becomes 0. So at steady state the equation is heat input equal to heat output. So at steady state, that is before the disturbance, T less than 0, and the steady state variables are xs and ys. At steady state the variables are xs and ys. So only the input at steady state, input equal to, there is no output, there is no accumulation. So only left hand side is HA into xs minus ys. That is the input. There is no output, there is no accumulation. So steady state equation is this: HA into xs minus ys equal to 0. So these are subscripts, x subscript s. This is y subscript s. Okay. So please note that this is subscript s. So this equation is HA into xs minus ys subscripts equal to 0. Well, now next we will subtract these two equations. Equation 1, so we have written unsteady state heat balance equation and steady state heat balance equation. So if you write this 1 minus, subtract this equation 1 minus 2, equation 1 minus 2 is going to give me this: HA into x minus xs minus y minus ys equal to mc dy by dt. So the equations, two equations, unsteady state equation minus steady state equation 1 and 2, 1 minus 2 will give me HA into x minus xs equal to y minus y of minus ys equal to mc dy by dt. And this dy by dt I had modified it as d of y minus ys, because ys is a steady state value, constant, steady state value. Xs also, xs and ys are steady state values, they are constants. So d of y I had modified as d of y minus ys. Now let us introduce the deviation variables, which are defined as capital X and capital Y. So capital X is the deviation variable in input, x minus xs, and y is, capital Y is y minus ys. So if we introduce these deviation variables into the previous equation 3, we'll substitute them into 3, we will get this equation. So for x minus xs, I substituted capital X. For y minus ys, substituted y. And similarly here, d of y minus ys is d capital Y by dt. So we have got a first order linear ordinary differential equation. So this equation this equation is a first order linear ordinary differential equation. Now how do we get this transfer function? Once you have got the linear differential equation which describes the process, how do you get the transfer function? Simple, take Laplace transform. Take Laplace transform of this equation. Take Laplace transform of this differential equation. So x, you have to remember, this capital X and capital Y are functions of time, x of t and y of t. So when you take Laplace transform of x, it becomes x of s. The x means x of t. This x means, capital X means is understood. L of x means this is L of xt, x of t. So L of xt is x of s. Similarly, Laplace transform of y becomes y of s. And this is the first order differential, mc into dy by dt. The transform of this is mc into s into y s into y of s minus y0. So this equation 5 is the Laplace transform of the first order differential equation. Now, what is this y0? Capital Y means what? Y minus ys. 0 means at t equal to 0. So t equal to 0, the disturbance begins at t equal to 0. Only after that, y varies. So at t equal to 0, the initial condition, initial steady state. At t equal to 0, y is having the initial steady state value. The thermometer reading at t equal to 0 was the same as its steady state value. So y equal to same as ys. So capital, so this is equal to 0. So capital Y of 0 equal to 0. So this term becomes 0. The initial value of the deviation variable. You can consider you have to consider this as the initial value of the deviation variable. So initially at t equal to 0, there is no deviation. So straight away this becomes 0. Now if you simplify this, taking y0 is 0, this becomes 0. Remaining equation, if you simplify, you get ha into x of s minus y of s equal to this. And if you rearrange, bring y of s to the right hand side, ys terms. So y of s into this ha plus mcs. And now, so if you find from this, if you find y by x, y by x, y by x, you find here, it is ha, this is ha by mcs plus ha. I just rearrange this, taken ys by hs. Now here denominator, I will make this numerator as 1. That means I am going to divide the numerator and denominator by ha. I will divide numerator and denominator by ha. So numerator becomes 1 and denominator becomes mcs by ha plus 1. So this is of the form k by tau s plus 1. This is of the standard form. This, if you compare with the standard form of first order transfer function is k by tau s plus 1. So this gives rise to a first order transfer function k by tau s plus 1, where k is equal to 1 and tau equal to mc by ha, where the gain, steady state gain k equal to 1 and the time constant tau equal to mc by ha. If you substitute the units of m, c, h, m is mass, kg, c is heat capacity, that is joules per kg Kelvin, h is heat transfer coefficient, it is joules per second meter square Kelvin, and area is meter square. So if you substitute all these units into tau, tau is mc by ha. So if you substitute the units, you will get the unit for time as second or any time unit. So this derivation shows thermometer is a first order system given by k by tau s plus 1. Gain, in this case the gain is 1 unit gain and the time constant is mc by ha. This condition, this derivation is applicable only when the assumptions stated in the previous lecture are satisfied. So you have to go through the previous lecture and followed by this lecture. So next lectures will study more about thermometer, mainly the response of thermometer for different type of input forcing functions. Stay tuned for those lectures, and I request you to kindly subscribe. If you like this, give your comments and share it to your friends. So see you till next lecture. Bye.